This is your presenter Asloob Mudassar, and I am presenting slide number 117 of the course on laser physics. Question: a laser can operate with a possibility of different transverse electromagnetic modes. Describe a method by which a fundamental transverse mode, that is a TEM00 mode, can be selected for operation. The answer is, it is always desirable to have a laser oscillating in the TEM00 mode, as large numbers of applications are associated with this mode. In a stable resonator, if more than one modes are present, for example TEM00, TEM01, TEM10, then to select the TEM00 mode, a diaphragm of suitable aperture size is inserted at an appropriate place along the resonator axis. The Fresnel number of the cavity, denoted by capital N, is associated with the radius A of the diaphragm through the relationship, that is capital N is equal to, that is the Fresnel number is equal to A square divided by lambda times L, where capital L is the length of the laser cavity. The diaphragm controls the loss of modes. A smaller value of A will drastically increase the loss of TEM01 and TEM10 modes compared with the TEM00 mode. Thus, by inserting a diaphragm of appropriate size in the resonator axis, one can enforce oscillations in the TEM00 mode at the cost of some loss. Selection of a mode in this way will require the laser spot to be small, for example 0.75 mm for a helium neon laser. For larger spot size, or equivalently for larger diameters of the active medium, the cavity Fresnel number is found from equation number 117.1, that is equation number 1, where A is now the radius of the active medium and its value should not exceed 2 as far as stable resonators are concerned. For larger radius, we speak about the unstable resonators, and equivalent Fresnel number is given by N equivalent, that is the equivalent Fresnel number will be equal to m-1 divided by 2, and this term is multiplied by the square of 2a2 divided by 4 times lambda L, where capital M and A2 have been described in figure number 92.3, that is in figure number 3 of slide number 92. So let me discuss that figure first of all, given in the appendix. This is the figure that has been referred in the text. The caption of this figure is a general two-mirror single-ended unstable resonator with spherical waves emanating from P1 and P2. So this is the diagram of an unstable resonator, and the spherical waves is emanating from P1 and P2. And this is a single-ended unstable resonator, which means that the output from the laser will be obtained only from one side, and here in this case obtained from the side where the mirror 2 is placed. So these arrows, that is this arrow and this arrow, will give you the size of the output beam coming out from the end of the mirror 2, and this is mirror 2 which is labeled by 2, and this is mirror number 1 labeled by 1. The diameter of this mirror is 2a2 and the diameter of mirror number 2 is 2a2. The diameter of mirror number 1 is 2a1. So you see that when the light from the P2 point is incident on the mirror 1, the light is reflected back towards the mirror M2, but with magnified diameter. And the magnified diameter after one pass will be equal to capital M times 2A2. So this is the aperture from which the laser beam of this size will come out, where capital M is the magnification of the system, and 2A2 is the diameter of the mirror 2. So you see that this figure explains for further detail you should consult slide number 92, and there you can find a greater detail of this figure. So where capital M and A2 have been described in figure number question 92.A3, that is in figure number 3 of slide number 92. If many modes are oscillating in an unstable resonator, then choosing an equivalent, that is the equivalent Fresnel number equal to half integer values, can increase the loss for other oscillating modes compared to the chosen mode. So you see that this is the condition that you should choose the value of n equivalent to be equal to half integers, that is 1 by 2, 3 by 2, 5 by 2, and so on. So this way you can increase the loss of other oscillating modes compared to the chosen one. Figure 92.7, that is figure number 7 of slide number 92, explains this behavior at half integer values of n equivalent. So let me show you this figure which I have reproduced in appendix, that is the figure number 92.7. This is the figure. The caption of the figure is plot of eigenvalue magnitude, that is sigma mod, versus the equivalent Fresnel number NEQ for the first three modes. So for the first three modes, this figure is given, and the first three modes are represented by the values L is equal to 0, L is equal to 1, and L is equal to 2. You can see that the magnitude of sigma has been plotted along the vertical axis, and the equivalent Fresnel number has been plotted along the horizontal axis. The three modes have been shown. You can see that a solid curve starting from nearly 0 point, zero value of n equivalent, the solid line, the solid curve actually represents L is equal to the 0, the first mode. The long dotted line gives you the mode corresponding to L is equal to 1, that is the second mode, and the third mode corresponds to L is equal to 2, shown with the small dotted arrows, a small dotted curve. So you see that if you want to select, you will notice that, for example, notice the peak value of L is equal to 1. This peak value will correspond to the value of 1.5. And notice that the peak value for L is equal to 0 exists at a value of 0.5, that is a half integer value. And for three half integer value, that is for 1.5 values of the n equivalent, the peak value of corresponding to L is equal to 1 occurs. And for the value of 3.5, you will notice that the peak of the L is equal to 2, L is equal to 2 profile, or L is equal to 2 profile occurs. So you see that these are the three modes. So if you choose the n equivalent value equal to 0.5, you are actually choosing the first mode, that is corresponds to L is equal to 0 mode, because this mode will then be converged towards the axis of the resonator. But if you choose 1.5, then you are going to choose L is equal to 1 mode, because L is equal to 1 mode will then be focused along the axis of the resonator, where the other modes will be much attenuated. That is, here the attenuation of the L is equal to 0 mode will occur, and will have a value close to minimum when we choose n is equal to 1.5. Similarly, if you choose 3.5 values, then of course the other modes will have smaller values there, and then you can choose the third mode. So in this way you can choose the mode of your requirement, and you will see that if you choose n equivalent from 0 to zero point 0.5, you will notice that the mode L is equal to 0 will increase. That is, it will keep on increasing, meaning that it will keep on focusing, or it will keep on propagating along the radial axis, along the radiator axis. And then you see that beyond the value of a 0.5, the values of L is equal to 0 mode will keep on decreasing, whereas the second mode will keep on increasing. In this way, by choosing the appropriate value of NQ, you can make some of the modes to decrease in magnitude, whereas some of the desired modes can be chosen to increase in strength. So the output beam of the selected mode has a ring shape. Ring shape mean, if you notice that the ring shape mean that the light coming will not pass through the mirror 2 if the mirror 2 is 100% reflector, but rest of the beam from this region to this region, or from this region to this region, the beam will pass out, and the beam will be stopped by the mirror 2 if the mirror is a 100% reflector. Then you see that you will have a ring shaped laser, that is a small hole in the beam in the center. The output beam of the selected mode has a ring shape, which is always undesirable. This defect can be corrected only for the lowest transverse mode, which is the TEM00 mode, by choosing an output coupler having a Gaussian or super Gaussian outward radial profile. So if you choose mirror 2 in such a way that it has a Gaussian or a super Gaussian profile, then of course you can choose this mirror, such a mirror for the TEM00 mode to be coming out from the end of the laser, from the end of the resonator at the side of the mirror 2 without any hole or without any ring. So a solid beam of TEM00 mode can be obtained. So let me read this last few sentences, that this defect, which defect, that is the ring shape, this is the defect in the beam. This defect can be corrected only for the lowest transverse mode by choosing an output coupler having a Gaussian or super Gaussian outward radial profile. So you see that I have tried to explain that how you can choose one of the modes, for example, preferably the mode TEM00 mode can be chosen. Here, and the other modes, that is TEM01 and TEM10 modes, can be attenuated in comparison with the TEM00 mode. And in most applications, the TEM00 mode is the desired mode. And you see that I have explained that how this mode can be obtained in the text. So this is the end of slide number 117.